All right, welcome to the third and final lesson of Chapter 3, Matter and Energy. This will cover sections 6 and 7, specific heat and changes of state. Also, at the end of this, this is the end of the first entire unit of the class, which is chemical foundations. And so as a result, you will have your first test. It will post tomorrow, and you'll have a week to complete the test. And you'll get more information on that and how to do the test and everything as that posts. Section 6 is specific heat. And specific heat is defined as the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. So for example, if we had 1 gram of water, it would take 4.184 joules of energy in order to raise the temperature by 1 degree Celsius or 1 Kelvin. So, raises H2O temperature by 1 degree Celsius or 1 Kelvin. Examples of specific heats are given in here for many different elements and compounds. You've got aluminum has a specific heat of 0.214 calories or 0.897 joules. Copper is 0.385 joules per gram per degree Celsius, and so on and so forth. And now the key thing to look for here is water in the liquid phase. It takes 1 calorie per gram to raise it by 1 degree Celsius exactly. That is actually the definition of specific heat. It really comes from water being 1 calorie, but it takes 4.184 joules to do that. Notice if we have solid water or ice, in order to raise its temperature by 1 degree Celsius, it actually takes less energy, and we'll see that later on in this lesson. Here's an equation that can be used to find the amount of heat required to raise the temperature of a known mass of a substance if you know its specific heat. The specific heat of the substance is SH right there. Delta T, that is the change in temperature. And M is the mass. All right, so we can use that equation to find the heat, or we could use a variation of it to solve for the specific heat. So if you know how much heat you've added to something and you can measure its change in temperature, you could get the specific heat. So normally heat is given as Q, and so you could say normally I'm used to it as ms delta T or MC delta T. It's crazy how many different ways people write specific heat, but I'm going to put S here. We don't need the H, it's redundant, but ms delta T is the way it's normally written as. It's not M delta T SH. So if you look at other textbooks or online for that equation, you'll normally see it like that. But we can solve for the specific heat by dividing each side by M and delta T, which yields Q, the heat, divided by the mass and divided by the delta T, or the change in temperature, equals that specific heat. So the first example of a specific heat question here says that Q equals ms delta T, where m equals the mass of the solution. If you react 50 milliliters of a 1 molar HCl solution, and this is 1 molar is defined as 1 mole per liter of a solution, with a density of rho equals 1.0 grams per milliliter, with another solution that's 50 milliliters in 1 molar but is sodium hydroxide, and it has a density of 1 gram per milliliter as well. At 25 degrees Celsius, the temperature of the resulting solution will raise to 31.9 degrees Celsius. How much energy was released? So when we look at this, this is an acid-base reaction. We're reacting hydrochloric acid with sodium hydroxide to make sodium chloride and water. Those are your products. What a chemist would do with this is realize, okay, I have an acid, I have a base. The acid is this, and the base is this. Those, when they're dissolved in water, are going to split up into their ions, right here and right here. And those ions will react with each other. So the H plus here and the HO minus over there will react with each other to make water. The sodium and the chloride, things that you won't really learn later, but you could if you took regular chemistry, they're not going to actually react with each other, so they stay as ions. And so as you can see down here, at the below that, oops, the chloride and the sodium plus, those cancel out. Ultimately, this yields this balanced equation here, where H plus and HO minus react to form water. And that's going to be important for this overall question here. But what we need to do is do the math, obviously. So we've got 50 milliliters. I'm going to do the acid. We've got 50 milliliters of it. Its concentration is 1 molar. So let me put V equals that. The capital M means molarity, moles per liter, and this is 1.0 moles per liter. The density of it is 1.0 grams per milliliter, and the temperature is 25 degrees Celsius. All right. Now for the base, we basically have the exact same numbers. We've got 50 milliliters, we've got 1.0 moles per liter. Your density is 1 gram per milliliter, and the temperature is 25.0 degrees Celsius. What we need to do here first, now that we've got this information, is find the mass of each of these compounds, the acid and the base. Well, since we have the density in 1 gram per milliliter, and we've got 50 milliliters, we can simply take the density is mass divided by volume equation, rearrange it to say density times volume is the mass, and so we've got 1.0 grams per milliliter times 50 milliliters. You can see the milliliters cancel out, and we get 50.0 grams of HCl. That means we also have 50 grams of sodium hydroxide. Now that we have the masses, we need to have the specific heat. So this is something we should already know, that since the reaction itself is ultimately forming water right there, that's the net reaction, we can say that the specific heat S or SH that your book uses is going to be equal to 4.184 joules per gram per degree Celsius. Okay. We also need to have the delta T. The final temperature is given to us in the question, and it says that after the reaction has occurred, it's 31.9 degrees Celsius. That means our delta T, which is T sub F minus T sub I, for the final temperature minus the initial temperature, is going to be equal to 31.9 degrees Celsius minus 25 degrees Celsius. And we get a delta T of 6.9 degrees Celsius. Now we have everything to do this equation. So Q is equal to the mass. Is it 50 grams or what? Well, if we take 50 grams of HCl and we have 50 grams of NaOH, do you think that's going to make 100 grams of water? The reality is it could be different, but we have 50 milliliters of a solution where the solvent is water, and for the acid and for the base. So really you do have what you could say is 100 grams of water. But the reaction is making more water, and so that's where it would get a little challenging. But let's ignore that fact because it ultimately doesn't matter here. Let's just say we have 100 grams of water in there, because the thermometer is going into the water that is surrounding the reaction. So that water surrounding it is going to absorb the heat and then give it to the thermometer. So the thermometer is actually measuring the temperature of the water. And so what we'll get here is 100 grams times 4.184 joules per gram per degree Celsius times 6.9 degrees Celsius. All right, and now we can check that. The degrees Celsius cancel out because it's in the denominator here, numerator there. And our grams are going to cancel out because we have numerator there, denominator there, leaving us with just joules. So 100 times 4.184 times 6.89, or 6.9. Sorry, I'm looking at two things at the same time. And this will be in joules. When you calculate this out, your calculator should show a number like 2,886.96, and again, the units are in joules, but you need to look at significant figures. All right, so everything we used here, we've got two significant figures. This actually had 3, the 50, because if you look really closely, it was 50.0 in there. I didn't write it in because I was trying to save space, but it is 3. So there's 3 significant figures on that. This is infinity. The temperatures, you're looking at decimal places because they're a subtraction. So they each had 1, so that leaves us 1 there, but we've got the 6, so there's 2 significant figures for 6.9. And the 100 was 100.0 since we added 50.0 to get those. So that right there is actually 4 significant figures. And so we have 4, we've got infinity, and we've got 2. So your answer should be to 2 significant figures, which means I'm going to look at the 2 and the 8. The number to the right of that first 8 is an 8, which means it rounds up. So we get 2,900 joules. That's not a decimal, there we go. Or you could say 2.9 kilojoules. Or you could convert it into calories, and you could take 2,900 and divide it by 4.184, and this is in joules, and that's joules per calorie, and the joules cancel out, leaving you with 690 calories, or 0.690. Whoop, I should fix this because I was making a mistake, a stupid one, but it's not an uppercase C calorie, it's a lowercase c calorie, which means it's 0.690 uppercase C calories. And that's how you do that problem.